Hola amigos! Today it's my responsibility to teach you electrostatics, and for that we'll be going through these stages. Too much to do, right? So what I've decided is I'll be making these sessions in parts. First part will be regarding the fundamentals of mathematical tools, that is some vector formulae, which is very important for not only electrostatics but also magnetostatics and other topics of electromagnetics. So also the next videos will be containing some laws and some formulae regarding electrostatics. After that, some for electric dipole, flux lines, dielectrics, and the last one will be containing boundary conditions and boundary value problems. I guess these videos will be short and interesting for you. So for that, let's begin with our first stage, that is some fundamental mathematical tools. But before that, let me tell you something, that the secret for being good or excellent in electrostatics or magnetostatics or anything is you have to be patient and give some time to it. Alright, so let's begin. These are some vectors, fundamentals and the formulae regarding them. And let me remind you one thing, that these should be on your fingertips all the time, because these are very important tools for solving any kind of electromagnetic problems. First thing, you identify this. I hope you have some idea regarding vectors. This is a unit vector which is given by the quotient of the vector itself and the magnitude of the vector. This symbol stands for the magnitude and this is the vector. A vector can be written in the form of, suppose this is my vector, I can write it as this. Now, these AX, AY and AZ capitals are nothing but the X, Y and Z components. And this small AX, AY and AZ are nothing but unit vectors. We call them as AX cap, AY cap or AZ cap. And let me remind you, these are in Cartesian coordinates. Now, the magnitude of a vector can be given by this formula, right? So, this is the vector we represented above here. And if we divide it by its magnitude, we get the unit vector, right? Now, what is a position vector? A position vector is nothing but suppose there are 2 points, say P and Q. Let the coordinates or the vector Q be represented as XQ, AX cap, YQ, AY cap and ZQ, AZ cap. And let vector P be represented by XP, AX cap, YP, AY cap and ZP, AZ cap. So the vector PQ will be represented as the vector Q, that is the position vector of Q minus the position vector of P. Now what is position vector? Position vector is nothing but the vector drawn from the origin to that particular point. Let me say, suppose this is our coordinate system. This is the origin. And now the vector drawn from origin to the point Q is nothing but the position vector of Q. Similarly, the vector drawn from O to P is nothing but the position vector of P. Now, there is something called dot product and cross product. Dot product of two vectors will give you a scalar quantity, while the cross product will give you a vector quantity. Right? So the dot product of a vector with itself is nothing but 1, but the cross product of a vector with itself is 0 here, right? So in our Cartesian coordinate system, or if any two of the vectors are perpendicular to each other, and if you take their dot product, then it will be 0 because they are perpendicular to each other, hence the cosine of the angle between them will be 90 degree, right? But in the case of your cross product, the cross product can be taken like this. You have to remember this matrix for fast and efficient calculation of cross product. This is something called the circle of life for the coordinate systems. Suppose if I take cross product of ax and ay, I'll be getting az and ax, I'll be getting ay, and likewise. But if I take the cross product of ay and ax, I'll be getting minus ax, az, minus ay, right? Because ax cross ay is equal to az, but ay cross ax is equal to minus az. They are not the same, right? Now, there are three kinds of coordinate systems. First is Cartesian, which we have just seen. Next is spherical, and the other is cylindrical. Spherical coordinate system is given by three components r, theta and phi, and cylindrical is given by rho, phi and z. Now, let me show you how they look. This is our Cartesian coordinate system, which you have seen. This is the cylindrical coordinate system. This angle of rotation in the xy plane is called as phi, or azimuthal angle, and the perpendicular distance from any point on z-axis is nothing but rho, right? So you can see if this is the z-axis, right? This is the z-axis. Then I hold my fingers like this. Then from each point on the circle of my fingers, these point, if I draw perpendicular to axis, that is somewhere here, then I'll be getting rho. So rho is nothing but the perpendicular distance from a point on z-axis, right? Now, this is the third coordinate system, that is phi, theta, r, or r, theta, phi. R is nothing but the radial distance from origin in any direction. Direction is important. Here it was perpendicular, here it is radial. And theta is nothing but the angle with respect to the z-axis, right? Let me tell you, theta can be between 180 degree and 0 only. Not more than that, not less than that. But phi can be between 360 degrees and 0 degrees, right? You have to be very clear with this. Now, the laws of dot and cross product, which are there for Cartesian coordinate system, apply for spherical and cylindrical as well. The circle of life for the spherical and cylindrical coordinate can be drawn like this. This is A. Here is the relation between rho, phi and z, and x, y and z, as well as r, theta and phi, and x, y and z. Right? These are used for interconvertibility. I request you remember them thoroughly. Now, these are the formulae or matrices for interconversion from your cylindrical coordinate system to your Cartesian coordinate system, or from spherical coordinate system to the Cartesian coordinate system. These are very, very important, right? Now, if I invert this matrix and I multiply it with ax, ay and az, I'll get a rho, a phi and az components. So, if I want to find a rho, a phi and az from ax, ay and az, then I'll just invert it and multiply it with this, right? Similarly, it goes for the spherical coordinate as well. Now, we have come to a very important concept called differential length, surface and volume. Now, differential length, as the name suggests, is a very small length or a very small surface or a very small volume. In all the three coordinates systems, Cartesian, cylindrical and spherical, we'll be seeing differential length, surface and differential volume. Right? So, in the Cartesian coordinate system, the differential length is given by dx, dy, dz. Suppose this is my coordinate system. Here are 2 points, but the distance between them is very, very small. Say the difference is dx, dy and dz. As we have done over here in finding this, the vector PQ. Similarly, let's say the points P and Q are very close to each other, then xq minus xp is nothing but your dx, yq minus yp is nothing but dy, and zq minus zp is nothing but your dz. Likewise, we find this vector, small vector dl. Differential surface is nothing but a very small surface. Let me remind you that the unit vectors with this surface x cap, ay cap and az cap are nothing but perpendicular, or the unit vectors of normal to the surface. A surface is defined by its normal, right? So, if I multiply my dy with my dz, right, then that surface will be lying in this plane, and hence the normal will be in direction of x-axis. Got that? Similarly, you can find for dx dz and dx dy. For dx dy, it will be lying here, and the normal will be along z-axis or parallel to the z-axis. Similarly, for the cylindrical coordinates, the small length, differential length can be calculated by d rho, rho d phi and dz. You got confused with rho d phi, right? Let me tell you regarding this. You remember the formula from your high school or 9th or 10th grades that the length of a sector in a circle can be calculated by the formula S is equal to r theta, where r is the radius, s is the length of a sector, right? Similarly, in our cylindrical coordinates, say this is a circle made of all perpendicular rows from this point of z-axis. Now, the length of this sector, say this, can be given by theta, which is nothing but r phi here, right? Multiplied by rho, which is nothing but r radius, right? So, in the cylindrical coordinate system, the components a phi, the component a phi will be, the component for a phi will be given by multiplication of this. That's what we have written here. So d rho, this small length d rho, d phi, small length, and dz, similarly as in the Cartesian coordinate systems. Now, regarding the spherical coordinates, you can see dr, the radial distance, small distance dr, r d theta. Similarly, as we calculated over here, r d theta will be nothing but this. And r sin theta d phi will be nothing but this, right? Because this is r. If I take the sine of this, I'll be getting a component somewhere here, right? And here, if I multiply it, I'll be getting this part, right? D phi, this will be r sin theta will be my radius, and d phi will be my angle. So I'll be getting this vector, right? R sine theta is my radius, d phi is a small angle here somewhere, and if I multiply them, I'll be getting a small length of a sector, right? So I got three vectors in terms of length. Now in terms of area over here, now I'll tell you how to imagine this. A rho cap, A y cap and A z cap. As we did there, the unit vectors, they tell us the normal to that surface area. So if rho d phi is one of the length of my area and dz is the other length, you guess in which plane it will lie, or where will it lie. Since it is perpendicular to A rho, this vector, our surface will be something like this, and this is the A rho unit vector. Got it? Similarly, you can find the others, and similarly you can find the other differential surface area in the spherical coordinate as well, right? The differential volume can be found out by multiplying all the components. This is very simple. You have to learn how to imagine this ds bar and dl bar, right? Now, line integral, volume integral and surface integral. Line integral is something with respect to the dot product of a vector with respect to a line or a small length dl. Volume integral is this is the volume density of something, and if I multiply it by a unit volume dV, I'll be getting the volume. And if I take a dot product of a vector A bar with a small area ds, right? ds, dv, dl can be calculated in all coordinate systems from here. Right? I'll be getting the surface integral, that is area over a surface, area over a volume, the volume, area over a surface, and the line length. This is length, volume and surface, right? You get the difference. Now here is the gradient, right? Gradient can only be calculated of some scalar quantity, that is v in all three coordinates has to be scalar, and this is the direct formula for it. For all the three coordinates, you have to learn them by heart and they should be on your fingertips. Similarly, divergence is nothing but del dot A bar, and these are the direct formulae for all the three coordinate systems till here. Curl is nothing but the cross product. Now is the del cross A bar of any vector, and here are the formulae for all the three coordinates: Cartesian, cylindrical and spherical. Divergence theorem. Now, divergence theorem is a theorem which gives the relationship between grad and dot product of a vector with a differential surface. Right? Sorry, this has to be A bar. To avoid the confusion, take this as A bar. This is divergence, that is del dot A bar. A bar dot ds over a surface, closed surface, is equal to the divergence of A bar, that is del dot A bar over a volume, small volume dV. Now, Stokes theorem. This gives the relation between the dot product and the cross product, that is del cross A bar, curl, and dot product of a vector a bar over a differential length dl cap. You have to remember these are very important for solving the problems so that you can find the relationship between them. Laplacian. Laplacian is a very important tool. This is the direct formula for it. It is also called as del square V. The symbol is called as del. And these will be using in boundary value problems. Right? So that's it for the fundamentals. Hope seeing you again. This is Shrey Ostwal signing off, and please comment how did you like the video, was it good, fair or not, so that I can make improvements in myself and present you the next video regarding our electrostatics, which will be beginning with the next video in the next session. Thank you.